Welcome to learning module number 7, corrosion control. In this module, you will learn a number of tools that allow you to either prevent or control the corrosion process. And I'd like to begin this lecture with something that metals have a natural tendency to do, and that is to form an oxide layer on their surface. In other words, metals and alloys, they can react with the air to form external oxides. And the reason this is important because for certain metals, that oxide layer that naturally forms on their surface can serve as a protective layer from the corrosion. Okay, so then the oxidation partial reaction is going to occur following this formula, something that we've seen before a lot, right? So this is basically a dissolution of metal or generation of metallic cations. And then the reduction reaction is going to be something like this, which, keep in mind, includes just oxygen, right? Now, typically, how does the process occur? In the majority of metals, you typically have your metals. Let's look at this diagram on the left-hand side, right? So this is where the dissolution of metal occurs, or in other words, we can call it as the zone of metal consumption, right? Meaning that the following this reaction on top, we have these metallic cations that are produced and then they diffuse toward the outer surface, right? Along with their electrons. And then once they reach the outer surface, I'm going to use it as the pink, blue color. They react with the gas on the outer surface, and this is where the metal oxide is produced. Okay, so this is what happens, and that means that this entire area, right? Perhaps I'm gonna just shade it like here, like I will emphasize it right here, right? So all this area is going to be the oxide. Metallic cations are generated and then they diffuse through the oxide layer all the way to the outer surface where they encounter oxygen anions. Then they combine, right? And that means that these two combine, right? Boom and boom, and they produce metal oxide, right? And the metal oxide is formed on the outer surface. This is what happens with the majority of the metals. However, with some heavy metals, the process is a bit different. And let's start with the similarities first. So you still have this metal surface where the metal gets consumed, but this time, not metallic cations diffuse, but oxygen, and specifically the oxygen anions, diffuse toward the boundary where the metal is consumed, and there we have the formation of the new oxide. Okay, so in a sense, the only difference here is that the nature of the ions that are drifting and which way they are drifting, right? In most common case, we have metallic cations that are drifting to the outer surface, and then we have the formation of the oxide. And then with some heavy metals, you actually have the oxygen, right? And specifically the oxygen anions, right? Negatively charged oxygen ions diffusing through the oxide layer till they reach this metallic surface where the metal is consumed and the new oxygen is produced. And you're probably wondering, well, how did people discover, right, which way and what is moving? Very simple. The way you can do that is that you can take a neutral marker, okay, some kind of inert marker, and you can place it on the surface. And in the first case, because the oxide keeps building on top of the surface, on the outer surface, eventually you won't be able to see the marker because the marker will get buried. Whereas in the other scenario, right, which is a bit more rare scenario, because the oxide keeps forming deep at the metallic surface, right? That means that you will be able to continue observe the inert marker on the surface, right? And I will highlight here exactly what I just described, right? So in figure 8, we see that the metal diffuses in the form of electrons and cations across oxide film, right? And we call it cation diffusion. Whereas sometimes, right, in some heavy metal oxides, and specifically this is going to be your figure B, you have the oxygen ions, which diffuse to oxide metal interface. This is the one that is shaded as blue. And then, of course, the electrons, they diffuse to oxide gas interface, right? So they are moving in the opposite direction. They're moving in here, right? They're moving toward the outer surface. And this is why we call this process as anion diffusion. Okay, so, and as I said, why would you want to be aware of it, right? Well, first, it's a natural tendency of your metal to react with oxygen. And for certain materials, right, under certain circumstances, of course, since it's a reaction, it will depend on the temperature and many other factors that you are about to see. But for some of our metals, this oxide layer can serve as the protective oxide layer, right? And this is why sometimes once we develop the material and before we send it to serve, right, within certain construction or as a part of a certain object, sometimes we actually oxidize it, right? We develop this protective layer. And if that oxide layer is actually protective, then we send it to the construction because it allows us to slow down the corrosion process of that specific metal in the future. So, just as we've seen in the previous slide, oxides form on metals due to the reaction of with oxygen in air. Right now, we can actually evaluate the degree to which these oxide films are protective against corrosion, right? And we're going to consider certain factors. And I'm going to go one by one and I'll explain what they mean, okay? So first, I will start with the following is for every single metal, you can estimate something which we call a peeling bedworth ratio. You will notice that I often occasionally will shorten it to PB ratio, okay? Or sometimes I would just say PB, okay? Now, so what is it? This is a ratio where you have the volume of oxide metal consumed. So that's the metal, the ratio of volume oxide. Something is off with the way it's phrased after oxidation. Instead of showing it here, I don't like the way it's phrased here. Allow me to just show you the next slide, okay? Because I have it written here a lot better, right? So what is the PB ratio? This is basically a volume of oxide produced, right? This is going to be your metal oxide that is produced. That volume divided by the volume of metal that has been consumed. And that ratio, ideally, I'll start right away, you want that ratio to be as close as possible to 1, because if that ratio, meaning whatever volume I consumed of metal, almost exact same amount of metal oxide has been produced on the film. In that particular scenario, the oxide will, perhaps I shall say, may be protective because there are other parameters that you have to consider that I'm about to disclose on the previous slide. Now, since we are looking at this, I'll finish my thought right away. Of course, you can end up with a scenario where your PB ratio is either less than 1 or it's more than 1. And here's what happens. Let's think for a second. Well, if my ratio is less than 1, right? So that means that my volume of oxide that has been produced is less than the volume what I have consumed. And that means if I am to look at this metal, right, I'm looking at, let's say, at a pipe, and I'm trying to produce this oxide, but if my PB ratio is less than 1, your oxide is going to look something like this. It's going to look like patchy regions, right? Because whatever is produced, right, this aluminum oxide, I keep saying aluminum oxide, I'm rushing a little bit, doesn't have to be aluminum oxide. In the example problem that I've chosen, I will be talking about aluminum, but in here it could be any metal oxide, right? So this is actually your metal oxide layer, right? And you can clearly see that the metal oxide here is porous and unprotective, right? So this is what we end up when we have the PB ratio less than 1. Okay, now what happens if you have more than one, right? So in this particular scenario, I'm not sure I am a good artist to demonstrate it. Okay, I'll demonstrate it. So that means that the volume of oxide that has been produced is actually more than what has been consumed. And perhaps I'm gonna put this thing that kind of like falls off. So what's going to happen is that you don't have a smooth, nice layer. Instead, you have a layer that it's too heavy and it falls off. It cracks and it falls off. And so this is why typically the closer you are to one, the better, the more the adhesion of a coating is perfect. And in a sense, let's call it a coherent coating that has a very high chance to serve as the protective layer. Um, well, since I just covered it, why don't we jump to the problem and see how we can calculate this PB ratio in one of the example problems, okay? So in this example problem, I would like you to consider aluminum oxide, right? Which is going to be aluminum 2O3. And then the question is, would you expect that layer to serve as a protective layer, right? It's basically a yes or no question. The density of aluminum is given as 2.7 gram per centimeter cube, right? And then the density for aluminum oxide is gram per centimeter cube. Okay. All right. So as I said before, we're going to go by the definition, right? So we're going to make this conclusion. First step is to estimate the PB ratio because that would at least give us some food for thought, right? Because, and you will notice that the number is not going to be one, right? It could be 1 point something. And then once you are in that scenario, we need to go and do a little bit more of research to be able to definitively answer whether it's going to serve as a protective layer or not, right? But the PB ratio is going to be the volume of your aluminum 2O3 that is produced divided by the volume of aluminum that has been consumed, right? Well, how would I estimate the volume? I'm just going to have to take my mass and divide it by density. Density is given, but I don't know what the mass is, right? So I need to first write down the reaction where I can look at the moles. And then from moles, using the molar mass, I can go to grams, right? So I'm going to have aluminum which reacts with oxygen, and this is how aluminum oxide is produced. Now let me try to balance out this equation. Okay. Now it looks like 4 moles of aluminum, right, produce 2 moles of aluminum 2O3, right? And so that means I can actually estimate the grams, right? Because if I take my formula, and I will remind you that the molar mass of aluminum from the periodic table, I'm just pulling it out from the periodic table, is 26.98 gram per mole. And then the molar mass of aluminum oxide, I have to do quite a bit of math, right? Because what I have to do here is I basically have to, oh, and I have to calculate it, right? But think about it. I'm gonna have 2 aluminum, that means 2 times 26.98, right? And then that number plus, I'm gonna have 3 oxygen in there. You will have 3 times 16, right? And so, oh my God, I pressed the button. I pressed the wrong button. My calculator is not the best one for these purposes. So once again, I'm gonna have 2 aluminum, 26.98. Well, might as well write it down, right? So 2 times 26.98 plus 3 times, running out of space, 3 times 16. Now that number is going to be 101, and I'll keep it as is, 101.96 gram per mole, okay? So now that looks like if I have 4 moles of aluminum, that means, and I'm going back to this, my chemical reaction itself, right? So if I have 4 moles of aluminum, which is going to be 26.98, that means that that value is going to be 107.92 grams of aluminum, okay? So I need that much of pure aluminum to produce, how much of oxide would I produce? It's going to be 2 times 1.96, and that shall give me, luckily, I have it still plugged in. It would give me 203.92 grams of aluminum 203. Right? Okay, so now I know the mass. The next step is I want to jump to the volumes, right? Well, that shall be relatively easy to achieve, right? So how would I do that? I'm going to start plugging it in the final equation. So I know the mass of aluminum, right? I have slightly above 100 grams. And I also know the molar mass and I know the density. And I only need the density. Okay, so to estimate the volume, I'm going to start with the mass of my oxide, right? And this is going to be in grams. And I'm going to divide it by the density of aluminum oxide, which has been given as 3.7. Please keep in mind is that it does depend on the source, on what you're using. You may, if you are solving this problem and using a different reference, you may notice that aluminum oxide may be given as a slightly different value, right? And it will change your final answer a little bit. Okay, and now I'm going to divide it by the 107.92 grams divided by 2.7 grams per centimeter cube. This number is dimensionless. Now I would like to estimate it with you. So I will have 203.92 divided by 3.7. Okay, and then that number divided by 107.92 divided by 2.7. Okay, and the number that I see on my screen is, I'm gonna round it up to 2 significant digits, and this is gonna be 1 point to 2 decimal places, 1.38 PB ratio, right? And this is the PB ratio for aluminum oxide. Okay, so now the question is, would you expect an aluminum oxide layer to serve as a protective layer? And let's go back to what we're given here, right? We're given the number 1 as the reference point that we should judge by, right? So clearly, the closer it is to 1, the higher the chance for the oxide layer to serve as a protective layer. And in this particular scenario, the aluminum oxide layer does have a very good, it is a coherent layer. But before, if you end up with something like this, right, 1.4, you do need to do a little bit of research, right? Because this oxide layer has been developed, has been tested, and the knowledge already exists. So whenever you are above 1, right, especially in a scenario like this, 1.5, 1.7, you do wish to do a little bit of more research, so you have some additional signs to rely on before you give the definitive yes or no answer, right? But hopefully it makes sense how you would identify it. It all comes down to estimating the PB ratio, right? And then just hoping that the number is kind of like explicit. Okay, but PB ratio alone is not enough, even though that this is what we usually begin with. Because if the number is 3, right, you do know that this is going to be a very heavy, chunky oxide layer that's going to fall off, flake off, and it's not going to serve as a protection, right? So we do often begin with the PB ratio, and the closer it is to 1, the better the protective properties. But there is also something else that we need to consider, and that is going to be next, is good adherence, right? And hopefully that makes sense, because you want these two to be like a single system, right? So that way, you want this oxide layer to be almost like a very, very strong paint that protects the metal underneath. You also would like to have a high melting point of the film, right? Now, low vapor pressure, you just want this coating to be coherent, good adhesion, and have the ability to stay put, right? Now, you also, what is very important is that you want to have the coefficient of expansion nearly equal to that of metal. So what does that mean? Whenever the temperatures of the environment change, right, whether it goes up or down, depending on that, your metal can either shrink or it can expand. And whenever you have a layered system, right, whenever you have a metal and then there's a coating on top of it, you want these two to act the same way. Okay, so you want them to expand as one and you want them to shrink as one. And why would you want to do that? Because if they expand at different rate, then there could be cracks produced, right? Or you can end up with some kind of like hollow spaces. And you don't want either of those because you obviously don't want any liquid trapped, right? And you don't want the metal underneath exposed because that's how you're going to create the perfect environment for either crevice corrosion or pitting corrosion, right? Just to give you an example, and sometimes you can have a galvanic cell. Um, Coefficient of expansion, I'll give you another example of this. When you want to have your system, right, to act as one. If you ever get your dental work being done now, right, especially I refer to filling, you should always pay for the best option they have, always. And it's not really about the color and it's not about the aesthetics. You want to put the material in your tooth that acts and behaves as a tooth, right? That represents the same expansion, right? And the compression. Because especially in our tooth, whatever, depending on what we consume, the temperatures change quite a bit, right? From cold to very, very hot. 50 years ago, or I actually don't really know, but there was a point in our history where people would use cement. And while cement does serve the purpose, but the reason it wouldn't stay long in the tooth is because it has a very different coefficient of expansion compared to the tooth itself. And so what happens is that if the tooth expands and the cement doesn't expand to exact same size, then there is going to be a crack or a space filled, a void in between the two materials that gets filled with debris, and this is how you basically lose a filling. And the moment you lose a filling, you also see that there is another cavity underneath, right? It's just a useful concept that you should keep in mind is that coefficient of expansion is a very, very powerful thing that you should always be aware of whenever you are trying to code anything as to protect object with some kind of like coating, right? Now, the the coating should also have a high temperature plasticity and the purpose of it to prevent fracture. And then the final point is that it should have low conductivity and diffusion coefficients for either metal ions or oxygen. And it makes sense, right? Because you want the coating, like once that coating is produced, you don't want the coating to conduct either metal ions or the oxygen, right? Because if you allow the flow of either of those, you will end up dealing with this process, right? You will end up with the material uh, being consumed over time, right? So hopefully that makes sense. Um, Another thing, if you ever paint anything, right, which painting could also be a very good protective coating. Again, it is beneficial always to have a thin layer that has a very good adhesion versus something that is chunky, that has bulbs and that has layers, because what happens, so basically the less the better perhaps in this scenario, because when if you go by more the better, you will end up with things that crack, things that fall off and expose your material. And of course, if you do have a scratch, right, if you have a dent, then that is going to be a big, big problem. Later on, I will actually show you examples, what kind of corrosion is going to kick in right away, okay? Now, we solved this problem. A little bit more on the oxidation rate. Typically, all of the materials the behavior of the oxide being formed on the surface can be described as three mathematical expressions, right? So it can be linear oxidation behavior, right? And that means that the weight gain, which is going to be your W, is equal to KT, right? Um, well, sometimes it could be no plus C wouldn't matter here. So it is KT, where K is some going to be some proportionality constant, right? And T is going to be your time. That K is going to define the slope, right? How sharp the slope is. But typically, the linear behavior looks something like this. Now, what does that mean with respect to the quality of the oxide layer itself? Well, metals may have pores, right? Like, for example, potassium where the PB ratio is actually 0.5, right? Or it can actually have cracked, very, very heavy coatings. Like for tantalum, the PB ratio is 2.5 oxide films, right? And then also at high temperatures, these metals with the linear oxidation behavior, they also tend to oxidize catastrophically, right? And you can envision that, right? Now, the parabolic rate behavior, where you will have the weight squared, right? Because you're looking at the parabolic behavior, and again, you will have KT plus C. At some point, you may assume that the constant, like in this particular scenario, the constant would be zero, right? But usually, this behavior is in metals with thick, coherent oxides, and this is going to be iron, copper, cobalt. Now, the last one is going to be the logarithmic rate, and perhaps I'm going to show you first the parabolic. This is your, makes sense to use different colors, so we don't, this is going to be your parabolic, okay? And then the final one is going to be your logarithmic. Okay, so slow and then steady. Okay, so with the logarithmic, the equation is going to look like this, right? And again, everything else is a constant except the t, which is going to be the time, right? And w again stands for the weight gain. And then what happens with these materials is that when exposed to oxygen, they tend to corrode fast, right? And that's why you see this at the beginning, we have like this upward, very, very sharp moment. And well, hopefully it makes sense. So I'm looking at the logarithmic curve. And then the corrosion rate decreases to a very, very low value. And you see that there's like a plateau. As time goes by, there's very, very minimum generation of material, right? And this happens with aluminum, copper, iron as well. Let's look at the example problem that you may encounter within this course with respect to the corrosion rate, okay? So we're given a 1 centimeter squared of almost pure nickel. It is also 0.75 millimeters thick. Now, it is oxidized in oxygen at 1 atmosphere pressure and 600 degrees C, right? Relatively high temperature. After 2 hours, the sample shows the weight gain of 70 micrograms per centimeter squared. So in a sense that, let's go the following way. The weight gain is going to be 70, and I'm just going to go with micrograms per centimeter cube, right? Micro is basically 10 to the power of -6. Allow me to write it down here in case if some of you do not recall that. So 10 to the power of -6. And what is the question here? If this material shows parabolic oxidation behavior, right? I'm going to go to the previous slide, and right away I will show you what we have to use, right? This is the equation where you have omega squared, right? The weight squared is equal to KT plus C. And I'm going to write it down right away here. This is what we're looking at, right? K is going to be some kind of constant, right? Which is unique for every single metal. And then T is time, and you have a certain constant here. The question, what will the gain be after 10 hours? Okay, so this is the weight gain at time equals to 2 hours. What is going to be the weight gain at time 10 hours? It's probably best to represent what I'm trying to estimate here. So if this is going to be my weight gain, right, and this is going to be my time, and let's say I have this parabolic behavior, and I know that at 2 hours, right, this is going to be my 2 hours. At this point, I know that I have a 70 micrograms per centimeter squared, right? Now, well, if the time is 10 hours, right, question is what is going to be the weight gain, right? So, well, since we know the weight gain and we do know the time for the first data point right here, this will allow us to find the k, right? The constant. Once I know the constant, I can find the weight gain at any time point because time is something that is you just define, right? So, and of course, I'm going to assume that this is equal to zero, and it makes sense because assume if a time is zero, right? If a time is right here, my weight gain is zero. And this is why I'm making this assumption that I can just disregard the constant. So with that being said, it looks like, so the K is going to be omega squared divided by the time. And for this particular scenario, it's going to be 70 squared, right? Ooh, okay, let me do the units right away. So it's going to be microgram squared divided by centimeter to the fourth. Okay, that's the weight gain. And then I divide it by the 2 hours, right? So what is it? Uh, 49, 240, right? Um, Yep. And the units will be micrograms squared per centimeter to the fourth per hour, right? Okay, moving on. What does it say there? Now that I have my K, I can actually highlight it, right? Because I can use it. Now I can easily find my weight gain at 10 hours, right? Because it's just going to be the square root of that number, K times T. And that's going to be just this number multiplied by 10, take the square root, um, and it's going to be 1.56.5. And the units, make sure that we take now I'm looking at these units right here, right? Since I'm multiplying it by 10 hours, by time, right? Hours cancel out, and now I'm taking the square root, so I end up with micrograms per centimeter squared, right? So this is going to be my final answer right here. Um, so again, in a problem like that, you will be certainly given the behavior, right? Um, and then from that moment on, you just need to do very basic math or algebra to find out the unknowns. All right, so now that we're familiar with the oxidation, right, the protective oxide films, we can move on to expand our toolbox to control corrosion process, right? So let's list what are the generic ways that you can apply to control corrosion, right? Sometimes prevent or mitigate. And then we go in depth with every single type of corrosion that we are familiar with and see what kind of tools are specifically applied with that type of corrosion. All right, in general, this is going to be applied to any type of corrosion. First one is material selection, right? And you can go with metallic or non-metallic. Something to keep in mind is that it depends on the process that you're designing. It depends on the industrial plant you work for, right? So this scenario is so unique, but usually as an engineer, right, you have an abundance of materials available to you, right? And so meaning that usually you are aware of the corrosive fluid that perhaps you will encounter in the process. And then you just can go either with metals if you have to, right? Sometimes if it's a food grade process, you have to go with stainless steel, right? And you just need to verify that the stainless steel is compatible with the fluids that you will be using there, right, to minimize the corrosion process. Now, often, if you don't have to go with stainless steel, you can save quite a bit of money and you can erase quite a bit of corrosion issues by going with non-metallic options such as plastics, right? Polymers, very cheap, very easy to make, and there's an abundance of them that would allow you to save quite a bit of money. You can also go with ceramics. Ceramics also have an exceptional ceramics, glasses, all of those have an exceptional corrosion resistance, right? You can also apply a coating, right? And then when it comes down to the coating, we have an abundance to choose from. You can use another metal, right, to deposit, to electroplate, but you have to be very careful, right? The quality of a coating, it's paramount that if you plan to rely on the coating, you need to make sure that the quality of that coating is superb and it will remain superb over many, many years of service. So you can go with metal, you can go inorganic or organic, and I think I have a few options here. So let's say if I am going with metallic coatings, right? So what I'm trying to do is that I am trying to take my material, right? And I'm going to separate it from the corrosive environment. Okay, and usually the metal that is on top, you want that metal to be your anode, right? So whatever is inside should be cathodic, and whatever is outside is anodic, because that means that the metal outside is the metal that will degrade. Now, if there is a scratch, right? If there is a dent, and if the material that is underneath is exposed, that material still won't corrode because it won't corrode till the outside layer is completely corroded, right? Because in a sense, you will have a galvanic cell, and even though the coating does have a dent, the outside metal is anodic and it will preferentially corrode while the inside material is cathodic, right? Now, usually such coating is applied through electroplating. We've already seen it. It's just like using the galvanic cell, or it can be a roll bonding, right? You roll it and this is how it picks up. It could have several layers. Now, let's look at the inorganic coatings, right? For example, very common, we take the steel and we coat it with glass, okay? Typically, we coat it with porcelain and then we line it with glass. Both of those have an exceptional corrosion resistance. Often, you may encounter tanks that are used for storage, and they have beautiful porcelain glass lining in there to make sure that the steel doesn't corrode, okay? If whatever we have inside is very corrosive to the steel. You can also use organic coatings, right? With organic coatings, we usually go with polymers, right? We use paints, we use varnishes, and then again, they serve as a barrier, but it is paramount that it should be applied carefully, right? Meaning that you can create a scenario where you chose a coating that is very porous, that allows the moisture to go through. Actually, one of the tragedies happened due to that. You don't see your pipe anymore because it is covered with what you believe is a protective coating, but in reality, you're trapping moisture underneath, creating this shielded environment, and just corrosion just is happening. You don't see it. By the time you see it, it's usually a massive explosion and a lot of people damaged, right? Okay, now let's move on. You can also control corrosion by design, okay? And I think everything I'm about to list here would make sense. Of course, you need to avoid excessive stresses, right? Just as an example, with if you're looking at the erosion corrosion, right, you should always avoid these very sharp bands, right? Like sharp bands in your pipes, right? Because you don't want the liquid to smash the walls because the thickness is going to be reduced a lot more due to this abrasive friction of the fluid cavitation, right? If we can avoid the formation of these bubbles, right, that explode like bullets, we should perhaps do that too. And it's going to be, again, it's going to be just a part of the, well, it's design and also in environmental control. Now, we should all obviously avoid dissimilar metal contact. We already know that. Never pair two things that are dissimilar, right? Because the moment you do that, you're gonna have corrosion happening, right? I'm sure that all of you have a lot of metals. Maybe if you have some kind of like a workshop in your garage, or let's say if you don't have that, maybe you have jewelry that you know that actually have different potentials. Once you put them together, just give it less than a week, and you will notice that there is going to be corrosion occurring on one of the metals right away. Um, you can also protect your jewelry the same way, right? Or it doesn't have to be a jewelry, it could be any metal, right? If you link it to something that you want to corrode, and whatever you're sacrificing will protect whatever you're trying to protect, right? Now, of course, you need to avoid crevices, because if you do have crevices, you're going to be dealing with oxygen concentration galvanic cells, right? And then exclude air. Hopefully people now are not surprised by this, and they would be like, yeah, that makes sense, because we did see quite a few of equations, right? At least two, where we know that air, and specifically oxygen, right, is a part of the reactant that you need for cathodic reaction to run. And if you can't quench cathodic reaction, you're going to be quenching the oxidation reaction too. Now, these two are paramount, and we will consider them in a separate video, because I really want you to be aware of the cathodic and anodic protection, because if you are ever to enter the corrosion industry, and if all and you at any point can, these are the two methods that are heavily applied industrially almost everywhere. So for that reason, we will consider those two in a separate video in detail. Now, and of course, you can control environment, right? Meaning that you can control the temperature, you can control the velocity, the oxygen, the concentration, the inhibitors, and cleaning, right? Or perhaps I shall say what the inhibitors are. Sometimes we can use certain chemicals that act as scavengers. They can consume certain species to prevent corrosion from happening. They can consume oxygen, they can consume hydrogen, and in either of those scenarios, you are slowing down the corrosion process. And then cleaning. Cleaning is really important, right? And why cleaning, right? Because it comes down to back to the formation of crevices, right? Because any metal that is underneath a certain debris will corrode. So my genuine advice, if you have a vehicle, right, and especially if you live in the environment where you deal with dust, dirt, and snow, you need to always make sure that your car is crispy clean, because yes, it will last you for many, many more years than a material that is standing in the dust, even a fine layer, right? So once again, because this dust, dirt, debris all creates a perfect, beautiful crevice corrosion, because the material underneath is lack of oxygen. So you're looking at the oxygen gradient galvanic cell that, trust me, will work beautifully. All right, now let's consider each of the corrosion. And even though we've covered every single type of corrosion, I do like to give you a short recall of what type of corrosion it is, and then we jump into the mitigation part, right? So uniform, we already know this is a general attack, right? This is a thinning and overall a thinning of the material, or the reduction in thickness uniformly across the entire area, right? So now, this also accounts for the largest quantity of metal loss. And then this one is one of the favorite types of corrosion, because it is the easiest to predict and monitor. You can see it, and you can easily estimate the rate of corrosion. And that means that you can encounter for that event that you are observing in the future. Okay, so what about the mitigation? What can you do? Well, first is material selection, right? And this goes without saying with every single type of corrosion. Second, thickness. Very, very easy. You can allow for the penetration of corrosion over time, meaning that whenever you are installing the pipes, and if you know the corrosion will occur at a certain rate, you can just change, you can choose the thickness of that pipe that would allow the pipe to be in service for 20 to 30 years before it has to be replaced. And this is a very common technique, right? Now you can apply coatings, right? And this could be either inside, it could be outside, right? Depending where the corrosive environment, where the aggressive corrosive environment is. And the idea of the coating is to limit the diffusion of the oxidizer to the surface of the metal, right? Because the moment we do that, we slow the rate of the corrosion. We can also use inhibitors sometimes. And once again, the inhibitors, it's a chemical that consumes one of the reactants, right? And you know that if the reactant is consumed, such as oxygen or hydrogen, that means that you are controlling the corrosion process, like you're slowing down the rate. Uh, Now you can also use cathodic or anodic protection, but whenever you see that, you know that there's going to be a separate video where I do want you to understand how those two work. Next one is galvanic corrosion, and typically it's one of the most, well, it is my favorite too. Whenever I see that type of corrosion, I get very excited. You'd be surprised how often you will now see galvanic corrosion happening everywhere, right? Whenever you see two metals together, uh, um, so first, it's not known as a bimetal, right? We know it as a galvanic corrosion. Some people call it bimetal or two metal, or in a sense, it's a dissimilar metal corrosion, right? So the concept behind it is a galvanic cell. I'm showing you another example of the galvanic corrosion here, and I really like this example because the reason you won't make a mistake, whether it's a galvanic corrosion or a uniform corrosion, you need to first ask yourself, do I see two metals paired with each other? And you can clearly see that both have been in service, right? None of them look brand new, right? But the difference here is that this guy right here is heavily corroded, right? Well, because that's your anode. Whereas this guy looks almost pristine, right? Like it feels like it is almost protected, even though the water is obviously the condensation, the air, the moisture is present for both, right? So, but this guy is going to be cathode, and it is currently being protected by the elbow, right? And whoever designed this elbow, you can imagine how dangerous it is if this goes undetected, right? Now, how would I mitigate it? Very simple. First is material selection. In this particular scenario, it's probably the one of the most important scenarios where you have to choose metals that have similar galvanic potentials. And you already know that you have many resources such as the galvanic series. Then you can look at to see, okay, what is going to be the potential difference between two metals? Are they compatible? Should I pair them together, right? Now you also have to be mindful of the area factor. I did mention it before. Specifically, you need to avoid large cathode to anode ratio, meaning that if you have a large cathode, you're providing a large surface for the cathodic reaction to run. And when you do that, that means that you are accelerating the corrosion of your anode, right? For that reason, avoid this area factor, right? Sometimes you can't get away by choosing a different material. Sometimes you just have to, there are two materials and you're stuck with them. You have steel and you have to connect it to the aluminum. You'll be surprised, but it is a very common practice where you just have to make these two materials work together as a part of a structure. So what would you do then? Well, you have to insulate these two materials, because as long as they are not touching each other, that means that they exist on their own, right? They will each corrode at their own rate, and meaning that they won't accelerate the corrosion of one or the other, right? And typically we use transition joints. And allow me to show you an example like that, right? So we're looking at the transition joint. So if you guys look at this, and I'm going to actually pair everything. So I have aluminum bolt, right? And allow me to kind of like highlight this aluminum bolt right here. So this is my aluminum bolt. I will take time to actually mark the colors. Now I have an aluminum plate right here, okay? And then I also have aluminum nut, right? Okay. And then the thing is that this aluminum plate has to be connected to the steel plate, okay? And I'm not going to jump to the galvanic series because hopefully at this point you've done quite a few exercises and you already know, while aluminum and steel, aluminum is going to be anodic, meaning that the if you are to quench those two, right? Aluminum bolt and aluminum plate, there's no concern for the galvanic corrosion, but obviously there's going to be a concern for a crevice corrosion, okay? Whenever you have anything that is kind of like threaded in, you will have a concern with the galvanic corrosion, but a crevice corrosion. But right now, my major concern is that if I am to take my aluminum plate and connect it directly to my steel plate, I will be creating a beautiful galvanic cell, right? And you don't need any moisture to be poured on it. The moisture in the air is enough to serve as the electrolyte, right? Meaning that your aluminum plate will start corroding, the aluminum bolt, everything, whatever is made out of aluminum and highlighted right now will be corroding. So how do I avoid that? Well, first, I'm going to use an insulating sleeve, right? You're going to put this sleeve. It is very common because that separates my aluminum bolt, and the aluminum sleeve is typically made out of polymer, right? And polymer is an insulator. So that means that now, even though I'm using aluminum bolt for my steel plate, those two are not connected electrically. In a sense, they exist as separate systems. Then I'm going to use an insulating mat between my plates, okay? And in addition to that, I'm going to use an insulating washer to make sure that there is no contact between my aluminum nut and the steel plate. I could give you an example like that in your exam. I can either ask you to highlight the area that has to be isolated, right? Or sometimes I give you a choice of the materials and I ask you to assemble a system. There's going to be something like that. So all you have to do is that if you do not happen to know by heart, okay, which one is anode, which one is cathode, at least you need to remember, okay, are they dissimilar or not, right? And if I do not remember, you will always be provided the galvanic series where you can find these metals to identify, okay, is there a difference, right? Because if there is no difference, you wouldn't be concerned about the galvanic corrosion. You would probably be concerned, let's say, if all of this was made out of aluminum, right? So I can remove all the insulating parts. That includes the mat, the sleeve, the washer, and what I would be concerned is crevice, right? So that means that all of a sudden I would need to close those crevices, right? Meaning that it's not about insulation at that point anymore, it's about closing the crevice, right? And perhaps using the bolt is not going to be the best way to do that, but we have a separate slide for this. Now you can also apply cathodic protection for galvanic corrosion, but again, at this point I'm gonna jump to the next portion because it will be considered in a separate slide. Next one is the crevice corrosion, right? What we remember about the crevice, you basically need a crevice, right? So this corrosion occurs because part of metal, right, is in shielded or restricted environment compared to the rest of the metal. And I'm giving here the example where you have this gaskets, right? And this is actually, I've chosen this example and you can clearly see that the crevice corrosion is happening in here, right? Because you have some of the metal that is shielded, right? So you're basically looking at the oxygen concentration cell. But then I noticed that this portion, right, this material right here, and this material right here, they're made from the same thing. I just realized that those two are corroding. They also happen to be connected directly, and they are also connected to the pipe. Those two are corroding because of galvanic corrosion, right? You can clearly see because you can see how you realize that. The middle portion, there is corrosion in the crevice and a lot of outside corrosion. It's actually the corrosion product, the corrosion debris that falls from above because there's moisture, there's condensation, so it sips underneath. But the two bands on top and below, you can clearly see that they corrode uniformly, right? Whereas the pipe is still whatever, it looks just like the pipe to the right. So this is a good example. During examination, I usually do not throw, whenever I give you a case study, it's usually very straightforward. There is usually a specific type of corrosion. I usually don't throw things at you where you have this and that. I just do that to make sure that we are not in the scenario where you mentioned one and then you didn't mention the other one. So it kind of like opens discussion, right? Whether you did good enough or not. So, so don't worry. If you spotted this galvanic corrosion here too, don't worry that typically you won't encounter, hopefully, examples where you have to be really on a lookout, okay? Usually it's very straightforward. Now, how do I mitigate it? Well, you typically, instead of, you need to use welded butt joints instead of riveted, bolted, or threaded joints. However, if you have to go with riveted, bolted, or threaded joints, right? It's any structure that has space there. And I want you to think of the fact that the space that for us looks like closed space, for oxygen and water, those guys are tiny. For them, it's a mansion to exist, right? This is what you have to be aware of. So this is why whenever there is a crevice, if you see just a line, right? There's just a tiny, tiny line. That is a crevice. It's a mansion, it's a penthouse for oxygen and water, right? So that means you have to close crevices by welding, caulking, or soldering. Right. Now, you also need to make sure that vessels drained completely to avoid debris buildup. Why this is important? Well, because just as I give you an example with the car, right? And even if you inspect your car and if you start looking, okay, where do I see the corrosion that is kind of like kicking in on my vehicle? You will notice that this is usually in the areas where you have either a significant impact of corrosion, right? It's the areas behind the wheel because of the centrifuge force, a lot of rocks, debris, dirt gets thrown onto the space. There's like a specific area in the car where you can see that there is a significant portion of corrosion happening, or it's going to be everywhere where you have a chunk of dirt hanging and you don't do anything about it. That means that you are there is an oxygen concentration galvanic cell that is running day and night until you remove it and you let the corrosion happen, right? This is why it is important. Now, you need to avoid the use of gaskets if possible, and it makes sense, right? Because you just need to, whenever you can, you need to avoid crevices, right? Or formation of any crevices. If you cannot avoid the crevice, you need to close the crevice, right? You should never leave the crevice open because it's just a matter of time till you will be able to visually observe the corrosion. Next one is a pitting corrosion, okay? So hopefully you guys remember it's a localized phenomenon, right? It's a very localized phenomenon, very destructive. And the reason it is very destructive, by the time you see the pit, you like right here, I'm showing you this beautiful examples right here. I'm not going to highlight it. I will show you this examples right here. It looks like a tiny dot, but in reality, it's a hole. And so if you are using that pipe to carry very, very high pressure gas, then you can see the gas pouring out of that pipe, right? So this is the danger I'm telling you about. So pitting corrosion is very destructive, very unpredictable because when you see a pit, uh, it feels like it's not a major concern, right? Some kind of imperfection. In reality, you should think of it. This is where the portion of the process can actually fail and it can erupt and crack and things like that, right? It is difficult to detect and predict because you guys remember that it's usually there's a pit that grows, there's a depth behind it, and you can't really know it. And that's a major difference between the uniform corrosion, right? Uniform corrosion is not deceiving. You can see it, you can measure it, you can predict it, you can calculate it. It's very, very stable. With pitting corrosion, it's very, very different, right? Now, the mechanism we already know. It's very similar to the crevice corrosion, right? We do know how the crevice happens. The corrosion happens in the crevice. Now, typically, this begins where there's a surface imperfection. And I don't want you to think of the surface imperfection as a scratch or like a dent in the protective film. All of this can be, right? But I also want you to think of the imperfection that can happen composition-wise, right? Whenever you have an alloy, right, you want things uniformly distributed. You don't want to ever have things that clustered and they're sitting as an island within your material. That's going to be your tiny, tiny spot of imperfection. Or it could also be just dislocation, right? So once again, scratch, break in protective film, compositional inhomogeneity, and things like that, right? Um, um, This is why, right? If anyone ever scratches your car, right, and they say, oh, well, that's not a big deal. But if you see that it's not their paint on top of your paint, if you can actually see that they did scratch your car, first thing you should do without even fighting with these people and making the wrong right, whatever, forgot what the saying is, but you guys get the point. First thing you need to do is that you need to take it to the service and you need to buff it out and you need to close it as soon as possible because that is a perfect example of pitting corrosion. Never delay it. I actually just got my car scratched and well, it's been a month. I haven't fixed it yet, but having this knowledge, keep in mind that a tiny, tiny dent in the protective coating, right, in the paint of your car is what gonna allow pitting corrosion to kick in. And once it kicks in, it's very deceptive, right? It grows inside, right? So what you see outside, it looks like a tiny line or a tiny dot, but in reality, the damage can be very, very significant. Now, so how would you mitigate the pitting corrosion? Well, avoid any inhomogeneity, right? And that means avoid the dents, avoid the cracks, avoid the dislocations, or avoid imperfections in your structure and things like that. And this is why we always pay more money for the metals that of a higher purity, right? That they have less imperfections there, for metals of higher quality and things like that, right? Because it's because you're basically paying to avoid the risk of pitting corrosion, right? And of course, the techniques that are valid for crevice corrosion are also valid for pitting, right? Okay, intergranular corrosion. Intergranular corrosion occurs, and I love this image, right? This is one of the best images I've seen of the intergranular corrosion. You guys can see how much space in between the grains, right? And that space keeps growing. Well, that's because there's a corrosion happening within the grain boundary. The grain boundary is anodic with respect to adjacent cathode and to a grain, and then the material within the grain boundary keeps disintegrating, and this is why under the microscope the spacing grows larger and larger, right? So it occurs anywhere where there's a potential difference between the grain and the grain boundary. Multi-phase alloys, we already looked at that, right? Whenever you end up with doping, right, you always need to make sure that whatever is introduced in the metal has to be dissolved and dispersed equally across the entire material. You never want to have chunks here and there because these islands can have a different potential with respect to the adjacent host metal, right? Um, Now, processes which contribute to changes in the alloy composition at the boundary include diffusion, right? So like some of the metals, they can actually diffuse out of the grain and they can diffuse toward the boundary, right? It can also be a reaction with other metals. It can be a reaction with non-metal compounds, and maybe you guys remember with weld decay, I did mention that you should always avoid any carbon content, oil, dirt, right? Anything that has carbon during the weld decay, right? Because the whole danger there is that during a sensitizing temperature, the chromium carbide can fall out of the precipitation, right? And you need chromium is a part of your stainless steel, right? But the carbon is what you can actually borrow from the outside, right? And that's why you have to be very careful. This is what we mean by the reactions with non-metal compounds. Now, significant cold working can contribute to this process too. Now, how do we mitigate it? And you will see that the majority of the mitigation is actually given with an example of the weld decay, right, which happens in the stainless steel. Well, first you need to avoid sensitizing temperature range, right? And hopefully people remember that's from 500 to 800 degrees Celsius, right? Because within that range, precipitation of chromium carbide happens at the grain boundaries, right? So meaning that the grains the area adjacent to the grain boundary starts disintegrating. Now, keep in mind is that you can use a heat treatment to redissolve chromium carbide, and specifically these are the temperatures are I'm giving here you in Fahrenheit. It's going to be about 1000, 1100 degrees C if you operate in Celsius, just like me. Now you can also add a stabilizer. So what it does is that, and specifically either niobium or titanium, adding either of those elements prevents the formation of chromium carbide. Right. Now you can also reduce the carbon content below 0.03%, and those we call low carbon steels. Um, but doing that is not enough, right? You also need to make sure that you remove any carbon sources when the steel is heated, right? And it's the oil on the hands, it's the oil on the gloves, it's just the rug that if a person who is doing welding is not familiar with this process, they can just wipe off the area that they are about to weld, and they do it with a oily rug, and you'll pay them for their service. They will be gone in less than a year. There's going to be a corrosion happening at the weld, and which is going to be your problem, right? This is why welding is something that requires high qualification, right? This is why it's a very well-paid job. Now, and of course, we can also use small grain size. Well, why? Because in a sense, whenever you have this small grain, you are trying, the intergranular corrosion is still a concern. But if I am to spread it all over my entire material, I'm trying to mimic like a uniform corrosion, right? Because it allows me to spread it evenly across the entire surface. Now, selective leaching. I promised you to show you some images. We're seeing some on the right. Before we go to the images, I will remind you that the other way to call it is going to be de-elementification, or the most common process is densification. Hopefully you remember that zinc and copper gets dissolved, zinc remains in the solvent, copper replates back, but the replated copper is very spongy, weak, and typically this is a good example of what it looks like, right? This is another example here too. Even though I chose these two examples, I always tell my students, whenever you see this color, right, this greenish tint, do not jump to the conclusion that you're looking at the selective leaching, right? Because you can just have copper corroding, and it also will give you like this green tint as well. So typically, whenever you deal with selective leaching, you need to make sure that you are actually looking at the alloy, right? Selective leaching only happens in alloys, right? Not pure metals. Um, so don't go by the color, rather go by identification of metal you work with, right? How do I mitigate this selective leaching? Well, very simple. First, you can lower the content of zinc, right? In a regular brass, we have 30% of zinc. Now you can use the red brass where you have 15% of zinc, meaning that you're dropping zinc by 30%, right? Now you'll be surprised, but most common technology is actually to entirely prevent it, right? Is to use very, and I mean tiny, below 1% amounts of tin, arsenic, antimony, or phosphorus. Adding those, right, or even one of those eliminates the problem in 70 to 30% brass. This is most commonly in the naval industry. You will be using brass that has, I don't know, 0.2% of arsenic in there, and just adding that tiny amount of arsenic eliminates the desensification problem. You can also use copper nickel as an alternative. What it means is that you still have the majority of copper, right? But then 10 to 30% is actually made of nickel instead of zinc. We do that, we use copper nickel in severely corrosive environment where brass won't be able to survive. Now, of course, you can also reduce the aggressiveness, and again, cathodic protection, skipping it for now. Erosion, without definition, I hope that people remember this is erosion happens due to the abrasive motion of the fluid, right? And I'll tell it again, the fluid doesn't have to be like a liquid. It could be sand, it could be slurry, it could be paste, it could be particulates moving, right? Doesn't matter. By fluid, there could be a lot of things, but the way we mitigate it, well, first, of course, it's going to be a material selection, right? You do want to choose the material that can withstand that type of corrosion, right? Sometimes there's no need to go with metal because you can be fine with just PVC pipes, right? It's going to save you thousands of dollars, right? And especially the replacement with time. Now you can use a better design, right? Um, What that means is that once you install the piping, right, you need to allow for the loss of thickness, right? Choose something that is thicker that will serve you 10 to 20 to 30 years before you need to change it, right? You also want to avoid sharp bends in pipelines. Hopefully that makes sense. You're avoiding this excessive stress, right, hitting the pipe. Now, you also want to have an ability to easily replace the parts that are expected to corrode, right? And these are going to be the joints, the elbows, and things like that. You want to be able to access them, remove them, replace them, so then the entire structure can still serve a lot longer, right? You can also alter the environment, and that means you can control the velocity, the temperature, the aggressiveness of the environment itself. Now, stress corrosion cracking. So typically with this particular corrosion, it's a combination of stress and corrosion, right? So you need to have corrosive environment and the stress. And typically you see it as the propagation of cracks in the metal surface, right? What we need to keep in mind is that usually when the stress corrosion cracking happens, it results in brittle failure of normally ductile metals. So we have in the corrosive environment, right? When subjected to a corrosive environment, keep in mind you need two, right? You need tensile stress and you need the corrosive environment. And here's an example what it usually may typically look like, right? This is actually an example of a stress corrosion cracking. Um, Often, you may see that the surface of the metal can be virtually corrosion free and you will just see these cracks. This will also be a stress corrosion cracking. Now, how would you mitigate that? Well, first thing, so because we know that there are two components to the stress corrosion cracking, right? And that is the stress and the corrosion or the corrosiveness of the environment. That means that we can alter both, right? We can either lower the stress, right? So what you can do, let's say if we talk about the residual stresses, right? These are the residual stresses that are introduced let's say during cold working, right? That means we can anneal the material, excuse me, to reduce to eliminate this residual stress, right? We can also thicken the section or reduce the load, right? Either reduce the load or thicken the section, meaning that it's kind of it reduces the load as well, right? Now, you can also alter the aggressiveness of the corrosive media. Just as an example, eliminate any critical species, right? Eliminate hydrogen, eliminate oxygen, and things like that. In both of those scenarios, you are reducing the aggressiveness of the corrosive media. We change the material when neither stress or environment can be altered. Just as an example, carbon steels are more resistant to stress corrosion cracking than stainless steels. So sometimes it makes sense to just swap the material. And of course, you can add the inhibitors. It's a part of altering the aggressiveness of the corrosive media, right? Because let's say adding phosphates or some other organic, inorganic inhibitors, the whole purpose is to eliminate. It's very similar to this point, right? These two are kind of related because it allows you to just basically alter the aggressiveness of the environment. Next one is hydrogen embrittlement, right? Just to remind you what happens is that the hydrogen penetrates the metal, right? And then the hydrogen reacts with the metal to form hydrides. And we know that the hydrides, they have a generally lower strength. Because of that, the metals have reduced strength and they're more susceptible to stress corrosion cracking. And I'm showing you an example here. You're looking at this crack. The reason the crack has been formed is due to the hydrogen embrittlement. So how would I mitigate the hydrogen, right? Well, first is that heating at low temperatures can reverse hydrogen embrittlement. So what you do is that even though you have this hydrogen, if you are suspicious that you may have hydrides formed as part of your material, what you can do is that you can use a low temperature heating to bake out the hydrogen, right? What happens is that you're going to break the hydride bonds, and then you can kind of like drive the hydrogen back out of the metal, right? Now, also very important here is to choose a material selection. If you know that you're choosing a material that will be servicing the area where hydrogen is present in either present or generated in high concentrations, you need to use alloys that are less susceptible to hydrogen embrittlement. And these alloys usually contain either nickel or molybdenum. Um, Now, you can also, again, keep in mind is that it all comes down to not allowing hydrogen to penetrate into your material, right? And that's why we also need to we can also use low hydrogen welding rods, right, and maintain dry conditions. And then the other thing is that we need to be familiar with is that during uniform corrosion, right, you can also have the hydrogen generated, right? Because if you guys remember that one of the reactions that we looked at was you have this H plus electron plus, and that makes this hydrogen, right? So in this particular scenario, you can reduce just the uniform corrosion, so you can slow down the production of this hydrogen, right? Now, hydrogen blistering, again, is very similar to the hydrogen embrittlement, but the only difference is that in the hydrogen embrittlement, we have the formation of hydrides that lower the strength of our metal, right, making it susceptible to stress corrosion cracking. In the blistering, we have atomic hydrogen that, again, migrates through the metal, and then it may enter the void where it stays long enough and then can combine with another hydrogen and basically form H2. And once this H2 is built up, if a void is increases, right, that void can crack as well. So how would I mitigate something like that? Well, you need to use high quality steel. Why? Because the whole idea is to minimize the number of defects and voids, right? Hydrogen is already tiny, right? And it doesn't have to struggle much to enter the material. So the less imperfections you have, the less defects and voids you have, the higher your chance for material to be less resistant toward the hydrogen blistering, right? You also can use coatings to minimize the hydrogen formation or migration rate, right? Again, you can use inhibitors to capture the hydrogen, right, and minimize the hydrogen formation. And you can use high nickel alloys that have smaller void space in the crystal because that allows to slow down the diffusion of hydrogen across the material. Okay, with that being said, we will conclude this lecture.